I bought this Heathkit IP-12 battery eliminator. It's a low ripple power supply capable of supplying 6 or 12 volts at up to 10 amps intermittently. This will give me the ability to service old car radios, tube radios with vibrators, and also solid state from the 60s, the early 60s. This is a capability I don't have right now. None of my power supplies will provide that kind of output. So it came in today, and let's take a look at it. First things first, we'll chop that cord off. It's a little dusty, but it's not in bad condition. The meter faces aren't cracked. They look to be in good condition. The switch is a bit stiff. Voltage control works. Timing posts seem to work. Fuse still in there. I don't know if it's the right size, but we'll find out. I do plan to restore this to working condition. This is interesting. We've got our rectifiers here. Looks like a full wave bridge. And we have our filter capacitors. They're going to need replacing for sure. There's a large filter choke, high current choke, big capacitors. These would be electrolytics. And this is the voltage control. We'll have to take that out and see if it needs servicing or not. Pretty simple circuit. I have a schematic for it. This looks like it's seen better days, but that's okay. It's all going to be replaced. 220 ohms, 2 watt. Wires are bus bar. Look like 14 gauge plated copper with sleeving. Pretty simple. Okay, well, we'll take her apart. See what needs to be replaced. Those capacitors have to go for sure. Okay, so that should free those up. Let's see if we can get these capacitors out of here. Okay, so we're going to take this lead here, which goes to the back of the fuse holder, and this is the line. Take that off. Pull that fuse out so we don't melt it. Alright, and this is our line. Keep the strain relief, a little Heathkit. And this goes where? This goes to the switch. Alright. And where does the lines go here? Oh, goes right to the ohm meter or the amp meter. Okay, good. Alright. Very clever. Okay, there's our choke. Need more spaghetti on there. Grand Transformer, Benton Harbor, Michigan. Nice looking piece of work. Okay, so this went to the fuse. This piece here. And this piece, this wire here goes to the switch. So let's take that switch out. So this is the secondary. This is the primary line, and this is the primary return. The way they wired this is kind of backwards because they've got the switch and the fuse on different legs of the power cord, which is not correct. But we'll fix that. Okay, now we're going to do a quick check of our diodes here and make sure they're good. We use our Heathkit component tracer, which is right there. And I'm going to put a clip lead on our common, on this diode set, and using 5 volts. Okay, this is good. It's a diode. The next one should be reversed from that. Reverse polarity. Perfect. Okay, next diode set. These are kind of weird because they're 2 diodes back to back, well, front to back. Okay, here we go. That one's good. this one's, oh, that one's not good. That one's open. Okay, so we've got 3 good diodes and 1 open, so we're going to have to replace them all. Just as comparison to show you how things have changed over the years, these 2 capacitors are 10,000 microfarads at 10 volts DC. They're electrolytics in big Bakelite containers, polarized. This is an Ichicon 10,000 microfarad at 16 volts. These are 10 volt. And look at the size of it. Now I'm not going to use these to replace those because I've got some fairly ancient computer grade Mallories here. 10,500 microfarad at 15 volts, and I happen to have a pair of them. Now I'm not a big fan of reforming capacitors, especially high voltage capacitors, but these are computer grade. They've never been used, they've never been installed, and they reformed nicely. They're not leaking physically or electrically. Now this is not a unit I'm going to use every day, so this is going to mostly sit on the shelf. It's going to be used occasionally. I'll never leave it running when I'm out of the shop. So I feel that these are safe enough to try at least. And the cool thing is they do fit in the old clamps. So I'll use a pair of these. And for this one here, this one happens to be 10,000 microfarad at 20 volts DC. Unless I find something more suitable, I have quite a few of these. This is 4,700 at 25 volts, 4,700 microfarads at 25 volts. So a pair of these in parallel will easily replace this 10,000 microfarad at 20 volt, and we'll have a 5 volt margin, safety margin. Oh, by the way, I did check the leakage on these with my Sencor LC102, and they are within range. They are lower than the maximum leakage allowed. Also, the ESR is excellent on those. The case doesn't look in too bad shape. It's a little banged up, a little bit. A few dings here and there. Paint's not too bad condition. Dent and a scratch. Well, let's see what we can do with it. See if we can clean it up. If not, we'll give it a fresh coat of paint. In our lab, we like to stack our instruments, so but I want to keep the handle together with the power supply, so we'll just attach it on the inside, and it'll always be there if we ever need it. So it came out pretty well. Looks good, nice and clean. There's a few scratches and a few paint chips, which is not critical. I don't think we need a coat of paint. I cleaned up the feet, cleaned them up. They came out pretty nice. Okay, so the case is solid and ready to go. Okay, this is a power switch. Looks great. Seems to work fine. Normally these switches are, this will be on and that'll be off. Hook up a bit of hookup wire here. It'll go to the fuse holder. And then we can mount the power switch on the front panel. And that should reach no problem. Okay. I like to connect the line coming in to the back terminal of the fuse holder. That way if the fuse blows, that's as far as the power goes. The front will not be energized, because the front is where the user will be most likely to touch. And if the fuse is good, and the line comes in here, you'll be able to actually get a shock. So, let's trim that a bit. I love Power Fist. Now this fuse is supposed to be 3 amp. This one is 6 amp, 250 volt. Alright, I think we really need to put in a 3 amp. Let's test this one, see if it's any good. Yep, it's good. We enlarged and reamed the hole for the Heathkit strain relief bushing and prepared the cord. And we should be able to insert it now. Should fit. There we go. So the line is the smooth lead. The return, the white, normally what would be a white wire in North American standards, is the identified conductor. So that's the neutral. And of course the green is the ground. And the ground needs to be bonded to the chassis using a screw that has no other purpose but ground bonding. So that's what we'll do here. We'll put it in one of the extra holes for the capacitor mount, the old capacitor mount. So this is primary one lead of the power transformer. The other one goes to the power switch. Okay, and the power switch, of course, is energized by the line through the fuse. A little bit of solder on this. Nice little bead. Straighten it out. Okay. Now this connects to the rear terminal of the fuse holder. That looks good. Now I'll just get a nut and bolt and we'll put this connect this ground lead down here to one of these spare holes. I've cleaned the knobs. I've replaced the power cord. As you can see, I've started to replace the power transformer, reinstalled it rather, and we have there's one bad diode in the bridge, and that's that one there. That would be it goes to 2. So 2 is D4. So this will be D4 and it's defective. So we expect on Monday, today's Saturday, so expect to get our delivery of our Schottky diodes on Monday. Our 220 ohm 2 watt resistor is across the new capacitors, which form C3 on the schematic. That's 10,000 microfarad at 20 volts. These are 10,000 at, which are 4,700 each at 25 volts. So they'll be fine. I've used some 12 gauge bus bar here, and on these I've used 14 gauge bus bar wire, which I got from a piece of Romex. Just use the ground wire. So these are the rectifiers on the heat sinks. There's 2 diodes on each heat sink. There's D1, D2, D3, and D4 diodes. D4 is open. The rest of them work okay. So what we're going to do is replace them all. I ordered from Amazon. I got 30, number 15SQ045. These are 15 amp Schottky diodes at 45 volt PIV, peak inverse voltage. That should be more than sufficient for this power supply. We're going to need 4 of them to replace these 4, so I'll just chop them off here. And we'll put the rest in inventory. I'm going to remove all the heat sinks in this bracket, and we'll have to drill a hole in the chassis, and we'll mount a pair of terminal strips on the chassis and we'll put the diodes, because we need to access both ends of each diode. So we have the anode and the cathode of this diode is attached to the heatsink, and then the anode of the bottom diode is attached to the heatsink, and then the cathode. So this will do it. We'll have a diode in between there, another diode here and here, and that'll give us access to all the cathodes and anodes of the diodes. So we'll mount that here. I decided to double up on the diodes. I've put two diodes in parallel for each of the 4 diodes in the original circuit. I think they'll run cooler and we won't have to worry about any failures going forward. So these are the 8 new Schottky diodes. So I've connected a load. I'm using my audio load up here, and I've got it configured for 4 ohms for each side, and I'm putting the 2 sides in parallel, so our total load impedance is 2 ohms, and it's capable of dissipating 480 watts. Now I've got the 2 meters set up. This meter measures voltage across the load, and this meter measures current up to 10 amps through the load. Now I have it plugged into my dim bulb tester here. The dim bulb tester has a variac and a bulb in series with the device under test, and also there's under the workbench there's an isolation transformer, so this is completely isolated, although it's plugged into a grounded outlet on the dim bulb tester. That ground is not connected to anything. I'm going to set the variac for about 118 volts. The dim bulb tester is connected in series with the load, so if this shorts out directly, the light bulb will light up. I'm going to turn on the variac right now. There we go. The light bulb is not lit, so I'm going to make it a direct connection. We've got 115 volts going into the device under test. The range switch is set for 6 volts. The voltage control is set for 0, and we're drawing 8.9 to 9 watts from the power line at 115 volts. I'm going to turn up the voltage control, we're on the 6 volt range, to about 6 volts. Okay, so we're just over 6 volts, as you can see. The 2 ohm load is drawing about 3 amps, which is correct. The meter's indicating just under 7 volts. Voltmeter on the Heathkit. The ammeter is indicating 2 amps. So these meters aren't terribly accurate, but they give you a rough indication of what's going on. Right now we're drawing 36 watts from the power line, which is just under 0.4 amps. Now I'm going to switch to the 12 volt range, and we'll see what happens here. Okay, we're at 9.5 volts output across the load. I'll take it up to just over 10 volts. We're drawing 114 watts from the power line, approximately. That's moving around. So we're just drawing a little over an amp. And everything seems to be okay. I don't smell any smoke. The diodes are all I'm just checking the temperature of the diodes, and they're just fine. They're just above room temperature. I would say they're less than 100 degrees Fahrenheit. So there you go. Everything seems to be working well. So just before this video, I performed a high pot test on the Heathkit, and it passed the test, no problem. I applied 1250 volts for 1 second to the current carrying parts of the device, and there was no leakage detected between the current carrying parts and the chassis of the device, so it passed the test. Okay, now we're going to measure the output ripple. The ripple for the 0 to 6 volt range, which we're on now, at maximum 5 amps continuous current. So let's set it up for continuous current of 5 amps. We're a little over 5 amps now. Because it's a 2 ohm load, the output is 10 volts. Now I've got a true RMS reading AC voltmeter here, connected right across the output terminals of the device, and we're reading 0.01 volts RMS. So let's work that one out. .01. I don't know if you can see that. Divided by 10.47 is the voltage, equals times 100 equals, I don't know if you can see that or not, 0.0955. So we're at 0.0955. And we divided by 100, so that's a percent. Okay, so let's switch to the 12 volt range. And the specification is, oh, it's the same. It's 0.3% ripple at 5 amps. So let's dial back to 5 amps. My meter just went to sleep. I hate these sleeping meters. Okay, let's take that again. This is let's adjust the current, dial back the current to 5 amps. And it's at 10 volts. So the ripple is 0.016 divided by the voltage is 10 equals times 100 to make it a percentage equals 0.16. I don't know if you can see that. 0.16. Okay, so we passed our tests. We have met our specifications. I'm just going to shut this off for now, and we'll take a quick look at the schematic. It's kind of an interesting circuit. Actually, this schematic in the manual is incorrect. There is a 220 ohm resistor across this capacitor, C3. Actually, you can see it on this schematic. They put the 220 ohm resistor in, and that's correct, but that's just a detail. The bottom line is the power comes in here, goes into our, this is voltage control, and the voltage control is transformer, and it has a slider. It's actually two, the secondary is bridged by, there are two secondaries and they're bridged by a contact, a sliding contact, which gives you a varying voltage across the yellow output leads, secondary leads. That goes into your 612 voltage switch, range switch, and connected to your diodes. Now, the interesting part is in 6-volt mode, the 4 diodes are connected as a bridge, a full wave bridge. So this is your output, and it's variable, and it goes through the bridge, and you've got your two buses. You've got your plus and your minus buses, and this is C1. This is your first filter capacitor. Now, when you switch to the range switch to 12-volt operation, it changes to the diodes change to a voltage doubler. They're put in series, and between the two sets of diodes and C1 and C2, it becomes a voltage doubler. And so on your bus here, you get a higher voltage, plus and minus, a higher voltage on your bus. The voltage comes out and goes, the voltage goes through the ammeter and either straight out to your unfiltered, it's partly filtered really, output, and through the choke and to your well filtered. So between the difference between the partly filtered and the filtered, well filtered, is really a choke and C3. C3 is a 10,000 microfarad 25 volt capacitor, which we put in. So there's your choke. That's what makes the difference between the two outputs. And your voltmeter is connected across your well filtered output.